Hello, this is Jude Socrates. Welcome to a portrait of linear algebra. Today's video is about coordinate vectors and matrices for linear transformations. Back in chapter 3, when we first saw linear transformations, we immediately saw that we can construct the standard matrix for a linear transformation if our domain and codomain were Euclidean spaces. But now that we have linear transformations of abstract vector spaces, it's not very obvious that that can be done as well. But of course, today we are going to learn exactly how we can do that. And notice that the article here is a matrix because there is no unique matrix for a linear transformation, as we will see in a little bit. So to do that, we will first need to learn how to construct what are called coordinate vectors with respect to a basis for the domain and for our codomain. And as I mentioned before, the main goal of this sequence of videos is to learn techniques in linear algebra, which will help us solve or find a solution for a differential equation in the near future. I corrected myself and said, find a solution, because we will not find all the solutions. Okay, spoiler alert. That is something which you will learn in a full semester's course in differential equations. Okay, so for our first step, we are going to construct coordinate vectors and coordinate matrices. We will use the uniqueness of representation property of a basis. So suppose that B, which is made of W1 through Wn, is an ordered basis for an n-dimensional vector space V. Suppose that V is any vector in V, then we know that this vector can be expressed uniquely as a linear combination of the vectors V. So we can write V equals C1W1 plus C2W2 all the way through to Cn Wn, and these coefficients are unique. There's only one solution to this equation for C1 through Cn. So we call the vector that these coefficients form, C1 through Cn, the coordinate vector of V with respect to B. Okay, so of course that is a vector from Rn. We can also turn this vector into a column matrix, right? So just put the numbers in a column vertically in the same order, and we will call this the coordinate matrix of V with respect to B. So notice there is a subtle difference in the notations. These are angled braces like we have for vectors, and these are square braces like what we have for matrices. All right, so let's start with a situation where the finding of coefficients is a very natural process. So we know that for Pn, the monomials 1x through x to the n, where n is the highest power that you are allowed in Pn, these monomials form something like a standard basis for Pn. Okay, so for P3, for example, we can use 1x, x squared, x cubed. Remember that P3 is 4-dimensional, not 3-dimensional. Okay, so we have 3 sample polynomials here from P3. Let's find their coordinates with respect to this ordered basis, right? So for the first one, it's very straightforward. Okay, the coefficients are obviously 6, and then we have -2, and then 4, and finally 7. Okay, 6 minus 2x plus 4x squared plus 7x cubed. It's just those 4 coefficients. All right, so how about this one? 3x minus 8x cubed. It's only 2 terms. Okay, so there's no constant. So therefore the first coefficient is 0. There is a 3x, so we put 3 there. And then no x squared, so we put 0 for x squared. And finally, negative 8 for x cubed. Okay, so those are our 4 coefficients. Okay, how would we write that as a coordinate matrix? Okay, so just put 0, 3, 0, and negative 8. Okay, so make sure you put them in the correct order. Okay, speaking of correct order, what happened to 5x squared minus 9x plus 2? Well, this is usually how we write polynomials, okay, from highest to lowest power, okay? So, if you want the coordinates with respect to this b, then you will need to put them in the correct order. So, 2 followed by negative 9 followed by 5. And there's no x cubed, so we put a 0 at the end. Okay, so in order to make this process fit into our goal of constructing a matrix for a linear transformation, it has to possess two properties that we like. Okay, so if you have any ordered basis B made of W1 through Wn, then the function t from V to Rn, which takes a vector and finds its coordinates with respect to B, is actually a linear transformation. So those two properties are additivity and homogeneity. Okay, so in particular, if the domain Rv happens to be Rn itself, and B is any basis for Rn, but it's a fixed basis for Rn, doesn't have to be the standard basis, then T is in fact 1-to-1 and on-to. Okay, in other words, it's an isomorphism for Rn. Okay, we're going to prove the additivity property, and I will leave the rest for you as a reading assignment. Okay, so additivity. We have two vectors in our domain V, and then we construct their coordinates. Okay, so T of V is this, which I have down here, and we have another vector U. Okay, so I just put it in alphabetical order. Okay, makes more sense. So the coordinates of U with respect to B are C1 through Cn. Okay, so we want to show that that T of U plus V, which means the coordinates of U plus V with respect to B, must be T of U plus T of V. But T of U is the coordinates of U with respect to B, and similarly for T of V. Okay, but let's remember, what do these coordinates mean? Okay, they come from uniqueness of representation. So U can be expressed as C1W1 through CNWN because this is our basis, capital B. And similarly for V, you have D1, W1 plus D2, W2, and so on. Okay, so now that you see this, you could probably do the rest. Okay, what is U plus V? Okay, well, add these two sides together, and then what's the logical thing to do? Combine the W1 terms, combine the W2 terms, and so on. Everything fits together nicely. Okay, so there you go. And of course, factor out W1 from C1 plus D1. Okay, and so on. So now, how do we find the coordinates of U plus V with respect to this basis? They're right there. We're looking at them. So this is the first coordinate, this is the second coordinate, and so on. Okay, so those are the coordinates in the coordinate vector, but obviously we can break that down into a vector sum. Put the C's into one vector and the D's into another vector. Oh, look at that. The C's are the coordinates of U with respect to B, and the D's are the coordinates of B with respect to B. Okay, so of course we can also show homogeneity. It's not hard at all. Multiply this by C. Maybe I should have picked another letter. Okay. How about K? multiply that vector by k, show that you can write the answer as k times the original coefficient. Okay, so to prepare ourselves for the big picture of finding a solution to a differential equation, let's bring back our space W equals span B, where B is made of these three functions. And remember, we made this in the last video because we wanted the smallest vector space, which is preserved by the derivative. Okay? In other words, the derivative of each of these functions is again a linear combination of these functions. Okay? So just a very short warm-up. Okay? Suppose we have this function, this linear combination. What are the coordinates of this function with respect to b? Okay? So again, this is very natural. So the coefficients are 7 and -8 and 2. Okay? So that is, of course, our last coefficient. I should delete that comment. Okay. What is the coordinate matrix? Okay, so write this now vertically as 7, -8, and 2. Okay, so we will bring that back in a little bit when we find the derivative of that complicated looking function. But now we are ready to put things together to construct a matrix for a linear transformation. So suppose that P goes from V to W, and we have verified that it is a linear transformation. We are going to fix a basis for the domain and a basis for the codomain. Okay, so for the domain, we have B, the vectors V1 through Vn, and for W, we have B prime, the vectors W1 through Wm. Okay, so based on this notation, V is n dimensional and W is m dimensional. Okay, so it's almost like we're going from Rn to Rm. Okay, that's what it should feel like to you. Okay, so now close your eyes and pick any vector from the domain V. Call it little v as usual. Our goal is to compute T of V, which is some vector W from the codomain, capital W. Step 1. Because V is from the domain, we can find the coefficients of V with respect to the basis B. Okay? So this vector together is what we were calling the coordinate vector of V with respect to capital B. Okay, so now we are going to use additivity and homogeneity to compute T of V. Okay, so we'll take T of both sides. Which will go first? Well, think of order of operations. We do the products first and then the sum. So when we break it apart, it's going to be backwards. We do the sum first and then the scalar products. Okay, so here we go. We have T of V on both sides. Take T of the linear combination, break down the sum. Okay, so we have T of C1 V1 plus T of C2 V2 and so on up to T of Cn Vn. Okay, now we can use homogeneity. Take out the C1 and we're left with T of V1. Next term plus C2 times T of V2 and so on. Okay. Next, we said that finding the coordinates with respect to a fixed basis is a linear transformation. Okay, so if I take the coordinates of T of V with respect to, which basis? Where am I? Well, T of V is from W. So we will take the coordinates of T of V with respect to B prime. Okay, We will do that to both sides of this equation. Okay, and then one more time, we are going to expand that out. Okay, what goes first? We will use additivity first, followed by homogeneity. Okay, so here we go. Scoot, scoot. Okay, so take the coordinates of t of v with respect to v prime. It's the coordinates of this long linear combination with respect to v prime. Break it up into a sum of several. Ooh, I haven't edited this yet. So I'm supposed to erase this. There you go. Okay. So we have the coordinates of C1, P of V1 with respect to V prime, plus the coordinates of C2, P of V2 with respect to V prime, and so on up to the last term. Now use homogeneity. We can factor out C1, factor out C2, and so on. We have this linear combination. Okay, so what is next? We want to create a matrix product, okay? Just remember, that's how linear transformations work in chapter 3, the first time we saw that. T of V is A times V, okay, where we write V as a column matrix. Oh, if only there was something here that we can put together into a column matrix. Ooh, how about the C1 through the CF, okay? But these are coordinates, all right? Well, they're only one step away from being turned into columns. All right, so let's do that. So we have that the coordinates, the coordinate matrix of T of V with respect to V prime is a linear combination of these coordinate matrices. Okay, so again, we just change the angled brackets to square brackets, and the equation stays valid. Okay, so there we go. We are looking at a matrix product. Put these column matrices into a single column matrix. I'm talking ahead of myself. I'm so excited. Okay, and put the coefficients vertically into a coordinate matrix. Okay, so there it is. Okay, so this right side is, that's column 1, that's column 2, coefficients into a single coordinate matrix. We will, of course, give this matrix a name, and let me show you the rest. Okay. So that matrix that we see on the right over here, we are going to call that the matrix of T with respect to B and B prime. Okay, so those subscripts, B and B prime, appear under the letter T. Okay, so we see B prime again in these columns, but the V's, V1, V2 through Vn, those are the vectors in B in the basis for the domain. Okay, so how do we use this matrix? We form this matrix product, and what we get are the coordinate forms, the coordinate matrix of T of V with respect to B prime. Okay, so there's a lot going on in there, and we will summarize all of that into this theorem. So suppose that T is a linear transformation from V to W, and the dimension of the domain V is M, and the dimension W of W, the codomain, is M. So let us fix a basis, capital V, V1 through Vn, for the domain V, and a basis B prime, W1 through Wm, for the codomain W. The M by N matrix denoted the matrix of T with respect to B and B prime, and given by the formula, in column 1, find the coordinate matrix of T of V1, the first vector in B, with respect to B prime, the basis for W. Okay, so compute T of V1, find the coordinate matrix of T of V1 with respect to B prime, assemble that into the first column of this matrix. Repeat the process for V2, repeat it for every vector in our basis, capital B. That matrix is called the matrix of T relative to B and B prime, or with respect to B and B prime. How do you use this matrix? Given any V from the domain, we can compute its image, T of V, via the formula, the coordinate matrix of T of V with respect to the basis B prime. It's just the matrix product of this matrix with respect to the coordinates of V with respect to the basis B. Now, in the special case when T is an operator, and of course it's only natural that we use the same basis B for the domain and the codomain, so B and B prime are exactly the same. Why shouldn't they be? Then we will just write the matrix of T, the operator T with respect to B, instead of T, B, B. That's a little bit of a redundancy. Alright, so computing T of V can be broken down basically into 3 steps. Okay? Encode, multiply, and decode. Right? So for an encode, choose your V from the domain. Find the coefficients of V with respect to B. So solve for C1, C2 through Cn that will create that linear combination for V. Okay, so in our examples, it was very simple. You're practically staring at the coefficients. And then we assemble the coordinate matrix. Okay, so next, use that coordinate matrix for the multiply step. Multiply this to the matrix that we found for T with respect to B and B prime. And what we get is the coordinate matrix of T of B with respect to B prime. Okay, so they are some numbers, D1 through Dm. Okay, these are C1 through Cn. Think of that as a vector in Rn. This is D1 through Dm. Think of that as a vector in Rm. Okay, so these coefficients are what we need in the decode step. Okay, those coefficients mean something. If you multiply them to the corresponding basis vector in B prime, the linear combination that you get is the answer that we want for here. Alright, so there are 2 examples in the 4th edition that walk you through this process. I'm only going to do one of them. So kindly look over, make sure you read it carefully, the example on page 415 to 416. It's about polynomials. What I want to do with you is about the derivative. Okay, so this was the example that we worked on earlier. We have this function as a linear combination of these 3 vectors. And so we found the coordinate vector and the coordinate matrix. Okay, so our goal, of course, is to find the coordinate matrix of the derivative operator with respect to the basis B that we have over here, and use this to find the derivative. Fancy, the derivative of this function. Ooh, okay. And you might say, big deal. Oh, please, I only need 1 minute to find that derivative. I know the product rule. I know the chain rule. I can do that. Okay. How about the antiderivative? Ooh, that's coming later. Okay, I'm just teasing. So, the steps are, we need to find the derivative of these three functions and put them together into a single matrix. In column 1, we have the coordinates of the derivative for this function, column 2 for this function, column 3 for this function. Oh, but wait a minute. Didn't we find those derivatives last time? Oh, yes, we did. And I have them hiding right here. Okay. So again, product rule, chain rule. Okay. So for x squared e to the minus 3x, take x squared, the derivative of e to the minus 3x is minus 3 e to the minus 3x. Second half of product rule, derivative of x squared is 2x times this function, e to the minus 3x. Simplify the answer. Repeat for x, e to the minus 3x. Repeat for e to the minus 3x. Okay? So, we are ready. We want the matrix of the derivative operator. Okay? So, the formula said, put the coordinate matrix of this answer in the first column. Okay, so by the way, we are going from W to W, and W is 3-dimensional. So our matrix should be 3 by 3. Okay, there you are. Right, so we'll go back to f of x in a little bit. So the rule said, put these coefficients into column 1 in the correct order. X squared e to the minus 3x goes first. So we have negative 3, followed by 2. Where is, oh, there is no e to the minus 3x by itself, so that should be 0. Okay, next, column 2. Put the coefficients of these into column 2. Again, x squared e to the minus 3x goes first, but there is none over here. So that should be a 0, a negative 3, and there's a 1 hiding right there. Okay? Last column. It's only this one term. There is no x squared. There is no x. So 0, 0, negative 3. Ta-da! All right. So that's the matrix of the derivative operator. Okay. So we're going to use that now to find the derivative of this function that we have over here. Okay. So let me copy that. Here. There we go. Okay, so step 1, encode. Oh, but we did this already over here. So let's just label that. Step 1. Okay, that is the encode operation. Encode. So there we have it. Okay. Step 2, multiply. Okay, so we will take this matrix and we will multiply it on the right by this matrix. Okay, so click and we get, ooh, that's the matrix product. Yeah, minus 21, 14 plus 24, yeah, 38, 0, minus 8, minus 6, minus 14. Okay, so last step, we will decode. Okay, so these numbers are the coefficients of x squared e to the minus 3x and so on in the same order that we use to assemble the coordinates for the original function f of x. So I can just copy this and replace the coefficients. So the first one should be negative 21, and then the next should be plus 38. And finally, we have minus 14. Okay, so that is the derivative of our function. Okay, so, yeah, if you like. we have achieved our goal. The derivative of our function is exactly. Okay, well, let's check. We have Maple, compute, calculus. We don't use that very often. Implicit differentiation with respect to. What's up with this? Oh, of course, it's in the wrong order. Minus 21x squared e to the minus 3x plus 38x e to the minus 3x. Right there. Minus 14 e to the minus 3x. Right there. Okay. Excellent. So, yeah, I was teasing you earlier with antiderivatives. Ooh, what's the integral of this function? Yeah, that's not a very fun exercise now, right? You're going to need integration by parts. So, very soon, we are going to be able to do that again using matrices. I'll just wait till next week. Okay, so I think that is our video for today. So thank you for watching. Oh, in case you're wondering, is my camera on selfie or not? Something seems to be backwards. Now the door to the closet is still there where it usually is. Everything's in its right place. Everything is where they're supposed to be. Okay, until our next video, enjoy the rest of your day.